Bayesian classification. So with Bayesian classification, this is a statistical classifier. So based on statistics, the probabilities of an object belonging to one class versus another. And so it's based on Bayes' theorem. And the neat thing about Bayesian classification is that it is incremental. So you can add more training data to the training set and continue to use your model. And so that's different than the decision tree, where if you add or increment into your training data set, you might need to restructure your entire tree. And so that's one of the benefits of using the Bayesian classification. So with Bayes' theorem, we have, let's say we have X is some data sample that we have, and we don't know what the class is. So this is the new data that we're trying to classify. So X in this case is a customer whose age is 35 and income is 40,000. And then we have H, which is our hypothesis that X belongs to a particular class. And in this example, it could be using the data where they bought a computer or not. So we're trying to classify, given X, what's the probability that they purchased a computer? What's the likelihood? And so we calculate out the probability, these are the prior probabilities, the probability of purchasing a computer and the probability of this particular customer. And then we have our posterior probabilities. So given that our hypothesis that they bought the computer, what's the probability of it being this type of customer? And the probability of, given this customer, the probability that they would buy this computer. So Bayes' theorem, we set it up for this probability that we're trying to calculate. We have the probability of H given X times the probability of H, the prior probability, over the probability of X, our prior probability. So one thing that's interesting about this for the Bayes classification, we'll see that we can ignore this denominator because it's going to be the same for all of them. And so we're really just comparing this numerator because for probability of all the different classes, we're still going to be divided by the probability of this customer. So we can simplify that process a little bit. So let's look at an example. This is a Bayes theorem specifically, not necessarily the classification. So here we have a doctor. We know that meningitis causes a stiff neck 50% of the time. So that's one of the symptoms. And we have a prior probability of any patient getting meningitis, and it's 1 in 50,000. And the prior probability that a patient having a stiff neck is 1 in 20. So if we have a patient who has a stiff neck, what's the probability that he or she has meningitis? So we calculate, for using Bayes' theorem, we would need to calculate the probability of having meningitis, that's a prior probability, the probability of a stiff neck, that's another prior probability, and then what's the probability given meningitis that you would have a stiff neck. And so then we want to calculate, well, given the symptom of having a stiff neck, what's the probability of meningitis? All right, so then we plug in our formula to get the result. All right, so then going back to naive Bayesian classifier, we have X, which is information about our customer or product, or depending on what we're trying to classify, and n number of attributes. So we could have their age, whether they're employed or not, their income, things like that. M is the number of classes that we're dealing with. And then our classification, we want to maximize the maximal probability that X belongs to a certain class. So which one is the highest probability? What class is it? So if we just have two classes, whether they bought a computer or not, which one is it the most probable? So based on Bayes' theorem, this is the Bayes' theorem formula. And here's where, because our P of X, the probability of our particular customer or product or whatever it happens to be, is the same for all the classes, we can really not calculate the denominator, we just have to compare the numerators. It's fine if you calculate the denominator, it's just a bit of a shortcut. So the naive assumption here is that we're assuming attributes are independent of each other. So one does not have an effect on another. So for example, something that is dependent would be like if I turn on the sprinkler, then the lawn is going to get wet. And so there's a dependency there. So we're assuming there's no dependency in between the different attributes for this classification. And so we'll look at another example with the Bayesian clustering that's going to handle it without the naive aspect here. Okay, so with this naive Bayes, when we assume attributes are independent, most of the probability calculations we need to determine whether the attributes are independent of each other or not. Are those attributes independent? So here's our example. We have the same data sets. We've been using the n is 14, whether or not they buy a computer. And those are our two classes, yes or no. Then we have a customer X, and the customer, we don't know whether they bought a computer yet. We're trying to predict. And so we have them listed as age is less than or equal to 30. Their income is medium, student, yes, and credit rating is fair. So we want to know whether they buy a computer. So we set up our formula here, and we're essentially looking for the probability of which class is highest, whether they bought the computer has a higher probability or not buying a computer, higher probability. So again, here's our formula. We can ignore the denominator because it's going to be the same across the board. So with our X being age less than or equal to 30, we have a bunch of attributes here. We have age, income, student, and credit rating attributes listed. So we're going to be calculating the probability for each one of those attributes given the particular class. So essentially we start with the prior probabilities, the probability that they bought a computer. So in our data set of n equals 14, we have how many bought a computer? There's 9 out of 14 that bought the computer. And then the ones that didn't buy the computer, it's the remaining 5 did not buy the computer. So these are prior probabilities on the class. So of the ones who bought a computer, so there were 9 that bought a computer, how many of them had an age less than or equal to 30? So these are age less than or equal to 30. Those are no's. Here's a yes, and here's a yes. So that's 2 out of 9. So we do that again for the second class, which was buys computer equals no. And then we go through all the variants here. So we're looking for probabilities based on each of the attributes of our particular customer. And then we end up combining through, given a particular class, what's the probability that we've got our customer here for yes or for no. And then we can calculate out what's the probability of them purchasing or not. So there's an example worksheet in Moodle that you can go through of more details on this example. So then we have one problem that sometimes comes up. One of the issues with this process is the zero probability. So with naive Bayesian prediction requires each conditional probability to be non-zero. And so what happens is we're doing this multiplication across in our formula. And so if we had something like income low, medium, high, and we had 0 in our data set for low, well, if we multiply 0 times everything else, we're going to get a 0 result. So the way to solve this zero probability problem is this correction where we add 1 to each case. So we do it across the board just to keep it even. So now low would have 1, medium has 991, and high has 11. So instead of being out of 1,000 tuples, now we have it out of 1,003 tuples. So it's really close to the original probabilities. So again, when we're working with large data, adding 1 is not really going to affect things. And then we've solved the problem of the of the 0 probability in here. So it's not going to be 0 now. So naive Bayesian classifier, some advantages: it is easy to compute. It's incremental, so we can add additional training data without having to change our model. And it's really good results in most cases. Some of the disadvantages deal with the inaccurate assumption of the class conditional independence. And so here we're saying that features are statistically independent of each other. So the presence of a feature in a class is unrelated to the presence of any other feature, which tends to be unrealistic with real world data. And so example here, when you have hospital patients, for example, with your profile, the age, family history, symptoms, diseases, there tend to be some dependencies in there. And so the naive Bayes classifier cannot handle or model this very well, the fact that there's dependencies across the board. And so you really need to use the Bayesian belief networks for handling that type of problem. So it is a good classifier, assuming there's this independence between the variables.